That's pretty loud. All right, so should be recording and can see the microphone moving. So let's just go ahead and switch over to the slides. All right, so today we're going to talk about performance metrics in machine learning. So you know, I kind of hinted at this as I was saying last time we met, because at the end we were measuring the performance of our classifier of predicting images. Okay, so but I only introduced one metric, which is called the accuracy, and I showed you guys how to calculate that, you know, kind of from scratch. However, today we're going to learn about the other metrics that are pretty important. We're actually going to learn that accuracy is not always the best metric. Okay, and so we have to really think about, so the idea of performance metrics is actually a little bit more complicated than it would seem. Okay, so that will be the objective. Close all these windows. I'm going to drain my battery. All right, so performance metrics in machine learning. So basically here to, you know, the objective is to, you know, have a better understanding of machine learning approaches and better understanding of the metrics. So the question is, what are performance metrics, right? Did it close? No. Okay. So what are performance metrics? Over there. So the idea is to have, you know, you need to measure how your model is doing in a quantitative way, right? So we need to have a score, and it's usually going to be a value between 0 and 1, you know, like a percentage. All right, so what you usually do is you divide the data. All right, that's the first thing. We've been doing this, you know, for a few weeks now, where we would split the data, right? We split the data into train and test at least. We can sometimes actually divide it into what is called train, validation, and test, right? Usually the majority of the data should be in train and then some data in test. In our case, we're basically not gonna need to create 3 data sets, 2 is enough. So we usually do train and test. So it's either gonna be like an 80%, 20% split, or maybe it's going to be a 70-30% split. Okay, that's usually what we've been doing, you know, in our analysis. So there's another one though, which is called the tenfold cross-validation. It's another approach to dividing the data. So in this case, instead of dividing the data into, let's say, 80% and 20% split, right? We're going to divide the data actually into 10 bins. Okay, so we're going to do like 1, 2, 3, 4, ... all the way to 10. We divide it into 10. And then what we do is that we perform the analysis or the training 10 times. Each time we hold out one of the bins as test. So what that means is, let's say, for instance, we're going to do this, instead of here, we only do it once. Here we do 10 iterations, right? So in the first iteration, we make this one the test sample. So we leave it out. That means we don't feed that data to the train set. And then we feed the rest, all of these, to the train section and build a model, right? Once we finish the model, we evaluate it just on this 10% of the data. And that's called one fold. Then what do? The next time around, the next time around, what we're going to do now is we make the second one the test set. That means that this one, this one, this one, this one, this one, you know, all of them, except the second one, are used for training. And then we train the model, we build a model, and then when it's time to evaluate it, we evaluate it on the second bin. Do you guys see that? And that's what is called tenfold cross-validation. So we hold one out, which is 10% of the data. And then at the end, for each iteration of the 10 or each of the tenfolds, we calculate the performance. Let's say we calculate the accuracy. So at the end of tenfold cross-validation, we end up with 10 accuracies, for instance. So we end up with 10 accuracies, and then we're just going to average it out or something along those lines. So that's the basic approach. Okay, so usually I'll show an example of tenfold cross-validation when we look at the Weka tool. But in general, when we are implementing things with deep learning, we're kind of just doing this. But we are sort of doing the tenfold cross-validation because remember that we repeat the process in the epochs, right? We do an epoch and then we go through the whole data set and then another epoch and go through the data set and then another epoch, go through the data set. And remember that every time that we read the data in each epoch, it's randomized. Remember that? And in a sense, it's similar to tenfold cross-validation. You guys see that? So we are technically doing it, if you actually more so than before. But tenfold cross-validation just refers to this. You know, it's like the non-deep learning approach. Got it? All right, great. So that's basically some of the ideas there. Now, what are the metrics that I was talking about? So the metrics are actually accuracy, which is the one that I showed last week. So you kind of have an idea of this one. You can actually implement this one in PyTorch, right? In PyTorch. Today, what I'm going to show is basically, you know, the equations for these, right? And after that, you should be able to implement the other ones on your own in PyTorch. However, to keep things simple, we're going to see that we can also do this in sklearn. And also you're going to see that, I mean, they can be done in TensorFlow and PyTorch. There's functions for that as well. And we're going to do it in Weka as well. So what are the metrics? All right, so the metrics are accuracy, there's, you know, precision, recall, there's the F measure, and then there's the confusion matrix. There's also the ROC curve, but that's not all the metrics that we have. Then after this, we have 40 more metrics, right? Many more, maybe 100 more metrics that are specific to different kinds of deep learning problems, okay, or machine learning problems. So for instance, let's say that you want to measure translation, right? So you build a deep learning algorithm that translates from English to Spanish, right? So how do you measure performance? Well, as it turns out, there's a whole bunch of metrics for that. One is called the WER, which is called the word error rate. There's a much more advanced one called the BLEU score. So what I want you to know is that every problem out there will probably have some metric to measure performance. And these are highly elaborate metrics, a lot of the time based on probabilities and things like that, but they're highly elaborate, okay? But for the standard classification problems, you know, like the ones we've been doing, you know, is it a cat, is it a dog? What you have to do for your term project with ADSB, exchange data, etc. We're just going to focus on these metrics. Okay, guys? Now, if you're doing linear regression, there's going to be yet another set of metrics that you're going to use, okay, that are provided specifically for that. All right, and so on. So, but for now, the standard metrics that you see in most machine learning papers, especially for classification purposes, are going to be these. And in particular, the most important one is the one called the F measure. Okay, that's going to be the most important metric that we have available. Now, the confusion matrix will be very interesting because it will provide some important insight and data. And this will become very nice when we start. We're going to look at, for instance, the iris data set with Weka that will very nicely and visually will help us to understand these a little bit better. Okay. So additionally, as I was saying, even though we're going to learn the equations today of how these work, and I already showed you how to implement accuracy in PyTorch, so you can easily implement the other ones. I will also introduce some additional modules out there that you might want to use. So for classifier evaluation, classification evaluation, we can use the sklearn.metrics module. So that basically, it's a Python library called sklearn. Obviously, that would need to be installed in your PyTorch environment. So something like pip install sklearn should probably work, or conda install sklearn. And this, obviously, as the name implies, provides some performance evaluation metrics. And there are, just like this, there's a lot of libraries. There's nowadays even something called the BERT score. For those of you that have heard about BERT, the huge transformer that's available, that was a few years ago, that was built by, I think, by Facebook or Google. And you can even use that to measure some kind of performance. So we'll show here how this module can be used with sklearn to evaluate our classifiers, whether TensorFlow or PyTorch. All right. What's great about using something like sklearn is that it's very simple to use. So instead of having to build the equations out, for instance, in PyTorch or TensorFlow, this will be a lot easier. So the names of those scores in sklearn are going to be accuracy score, recall score, F1 measure. So these are the actual names of the modules, precision score, and confusion matrix. Okay. Now, let's get into how these work, the equations, okay? All right, so we have our accuracy here. This is the metric that we learned about last week, and you kind of implemented it. However, to get a better understanding of it, it makes sense to create a little table such as this one. So in this table, what this table has, if you notice, is it assumes, first of all, just two classes, right? So this is a two-class problem where you either classify 1 or 0, okay? Then you have data, which is the true data. That is to say, you have the real labels, right? And then you have the predicted, right? What the model predicted. So if you remember last week, we were evaluating in the loss function predicted versus real, right? So what are the real labels versus the predicted labels? So what this table captures, this is called a confusion matrix. It captures, it divides the data. So for instance, true 1 implies all the real 1 samples, right? So for instance, all the images of cats, and this is all the images of dogs. So here you have A plus B, that's the quantity. So there are A plus B true 1s, right? And then there are C plus D true 0s, right? So that's the quantity, whatever it is. Here on the column side, we just say, how many of those did the model predict correctly or incorrectly? So for instance, what this means is, if it was a true 1, there were, out of A plus B, there were A that were actually predicted as 1. Do you see that, guys? Whereas, out of A plus B true 1s, A were classified as 1, but B, quantity B, were classified as 0. So that means they were incorrectly classified because they should have been, in this category. Do you see that? And that's the same over here. So we have 0 and 0. So that's correctly classified. That's D. And then C represents something that should have been a 0, but was classified as a 1. So it's a misclassification. Now, what's great about this confusion table is that given this table, we can calculate the accuracy, all right? Because we can see that the accuracy is nothing more than, for instance, for the whole thing, A plus D divided by the rest, by all of it. So we look A plus B plus C plus D, that's the whole data, right? Because it's the total of ones and the total of zeros, so that's all of them. But we just want to know the accuracy, which means which ones were correctly classified. Well, out of these 4, which ones were correctly classified? Out of those 4, which letters? A and D, right? Exactly. And that's it. So that's all you need to understand. And I think accuracy is pretty intuitive there. However, the other ones may not be as intuitive, right? So because we have the, I have an example that should explain it a little bit better, but we really need to understand this. These metrics are extremely important, and they're going to depend on what we're trying to solve, the problem that we're trying to solve. Let's take a look at the other one, precision, right? So in precision, you have A divided by A plus C. So what does that mean? First of all, let's look at A plus C. All right, A plus C is these 2, right? So what is that? And then A is just that. So we can almost interpret it as saying, out of all the predicted, let's say for class 1, right? Out of all the predicted, how many were correct? Do you guys see that? That's an important one because the model is telling you, there's all of these, but just these. Not all of those, just these. Well, you only look at these, but are they really? How many of these are actually correct? If you're looking for something of interest, that's important, and that's called precision. Got it? All right. The next one is called recall, and it's this one. And here, if you notice, we have A divided by A plus B. So what is A plus B? So if you look, A plus B is that, and A is this one. So what that means is, out of all the true ones, how many did you find? Do you see that? It's a little bit different. That means the recall, not from the predicted ones, but from the real ones. How many did you find? Got it? All right, and that's called recall. And all of these are important metrics to measure the performance of your classifiers. As it turns out, some classifiers, might give you really great accuracy, but when you look at it, it's meaningless, especially when you have what is called a highly imbalanced data set. And what does that mean? Well, think of the problem of fraud detection in a bank. How many transactions does a bank have in a month or a year? Millions, right? Millions of millions. Most of those are legitimate transactions. There's no fraud there. So fraud cases are actually going to be a very small fraction of those millions of transactions. So if you have a problem where you're trying to find transactions and you're trying to train your machine learning algorithm to identify fraud versus non-fraud, you have most likely like 99% one class, 1% the other class. Accuracy will not give you a good result there. You have to take a look at precision and recall to get a better view of the problem. Do you guys see that? Any questions so far? All right. So what is F measure then? So F measure is defined as the harmonic mean between precision and recall. So what that means is that first you're going to calculate precision and recall, and then you join them together with this equation. And what that basically means is that the F measure, if we want to think of it intuitively, it looks at both precision and recall and tries to find a balance. So it tries to find something, because it's not, you don't necessarily want something that has really high precision, because then it might have really bad recall, or the other way around. So what you might be looking for is something that has good precision and good recall, a good balance of both of them. And that's why the F measure, sometimes called also the F1 measure, is a metric that you see a lot in research papers, especially in classification problems, right? So whether it's binary like this one or multi-class, as we will see later on, it doesn't really matter, but it is, it's a good metric. Any questions so far? No, making sense? Okay, good. All right, and then the confusion matrix, this I took from Weka itself. We'll do this exercise just so that if you've never seen, how many of you have never used Weka before? Raise your hand if you, okay, so the majority of you, okay, all of you. So that's such an easy tool that it takes like 15 minutes to learn how to use it, but I highly recommend it. It's not for big data, but it's usually the kind of thing that, let's say you have 2 million records or something. Randomly select 100,000 of those, run them through Weka. It's a great idea, okay? Because it gives you a really big picture of what's going on. If you randomly select 100,000 from your data set, let's say you do that 10 times, and basically you're going to start to see a pattern of your data, even though you're not looking at the 2 million records as a whole. You guys see what I'm saying? So it's a really great tool, even though it's kind of, limited, constrained a little bit, but like I said, just grab, I think it'll handle like 100,000 by 10,000. Any matrix that is less than 100,000 by 10,000, it'll handle it easily. And so it's really good at visualizing data. I kind of like it. So we'll play with it a little bit today. So anyway, what is the confusion matrix? So the confusion matrix is very similar to what these tables are, right, that we were looking at before, except here I have one where we have 3 columns instead of 2. So here, this is the iris data set, as you can imagine by the name. So this is the iris data set. You can see that here. And we have 3 classes for it: Setosa, versicolor, and virginica. And then basically, what we're saying is in the confusion matrix, if it's class A, how many were classified as A? Well, as it turns out, 49 were classified as A, 0 as B, 0 as C. That's a good, it tells you there's, didn't make any errors, basically. For versicolor, we have, it's B. So how many were classified as B? Well, 46, but 4 were misclassified as C. So there was a total of 50, and it only misclassified 4. Here, for virginica, the class is C. So how many were classified as C? Well, 46 and 4 misclassification. Do you guys see that? And that's the beauty of Weka. Remember, it, you can give it any data set. It's going to randomly select it. You can do the splits and everything. So I usually, when I do this lecture, I like to introduce Weka as well, as it's just another tool for you to use. Got it? All right, great. Now, round 2. So round 2 is meant to be a more detailed problem to kind of motivate the importance of precision and recall. Okay, so this is the classic example of, you've probably seen this before. You do this in in the statistics community does this a lot with like healthcare, right? So it's the same problem of detection of a disease, right? They do an exam, etc. So here, instead, I'm going to do this one, but with like cybersecurity. So we're going to talk about, an example here. So for instance, detection of terrorists, something like that. So would you believe someone who claimed to create a model to identify terrorists trying to board flights with greater than 99% accuracy? What would you say? So if they come and they sell to you this model and they say, this model has 99% accuracy, would you buy it? You'd probably say, oh, that's pretty good, right? I'm gonna buy it. And so you would think, yeah, you say 99% accuracy is probably really good. But really, if you look at this model, if you really study it, you're gonna see that it's meaningless what they're saying with 99% accuracy. If you think about it, let's break it down. So here's the model. Simply label every single person flying from a US airport as not a terrorist. Given the 800 million average passengers on US flights per year, and the 19 confirmed terrorists who boarded US flights between 2000 and 2017, basically this model would achieve 99% accuracy, 99.999% accuracy. Why? Because 800 million versus 19. Yes, there's two classes, terrorists and not terrorists, right? So if you just label everybody as not terrorists, that's 800 million. Think about that, right? So there's, 19 out of 800 million versus, what is that, 7, or let's just say 800 million. And this is also like minus 19, 800 million, right? So it's a pretty large number here versus this one, which is going to be pretty small. All right, so accuracy is going to be meaningless for you. Okay, so therefore, you don't buy it, right? So you need to find another way of measuring performance. And that's why we look at precision and recall. So that might sound impressive, but the US Department of Homeland Security may not be calling anytime soon to buy this model. While this solution has nearly perfect accuracy and might sound convincing, this problem is one which accuracy is clearly not the adequate metric. Okay, and that's the point. So the terrorist detection task is what is called an imbalanced data set, right? And this will be one of the big problems you're going to encounter, right? So right now, for instance, we've been using CIFAR 10, we've been using MNIST. Today we'll probably use IRIS. Those data sets are balanced. They're highly balanced. They're made for the results to look really pretty and nice, and for you guys to learn, understand how things work. ADS-B exchange, the data that I gave you for the term project, for part A of the term project, once you're going to pick a problem that is of interest to you. Once you start filtering the data and you start to look at it, you're going to see that it's not going to be balanced. For a lot of you, it's going to be very imbalanced because that's the reality, right? Otherwise, everything would be easy, right? If you want to make money in the stock market, majority of the data is going to be noise, it's going to be useless, and there's only a little tiny bit that's what you want. Finding it is hard. And that's kind of the classic example of imbalanced data sets. So there's a lot of techniques out there for dealing with imbalanced data sets. But right now, the key thing to understand is that accuracy, whenever you tell me a score, like you tell me, oh, the accuracy is this, you'll hear me say, always, talk to me about your data set. How many classes? How many samples? What's the balance between the classes? And I'm going to start digging in to kind of figure out if your accuracy score is actually meaningless. You know what I mean? So for instance, when you do your term project at the end of the semester with ADS-B exchange data, right, the flight data that I just showed you, you're going to say, oh, no, my accuracy was 70%. But that's not enough, or, it might be meaningless, right? Until I understand what your data looks like, how you divide it to classes, etc. Got it? All right. So here we have just two classes that we need to identify, which are terrorists and not terrorists, with one category representing the overwhelming majority of the data points. You know, what is it? 800 million minus 19, right? That's one class, and the other one's just 19. Another imbalanced classification problem occurs in disease detection, which is what I was talking about. If you've taken a statistics class, I very likely you looked at this from that point of view, you know, cancer detection, something like that. You know, this is the same thing when the disease detection, when the rate of disease in the public is very low. In both these cases, the positive class, disease or terrorist, is greatly outnumbered by the negative class, non-disease or non-terrorist. These types of problems are examples of the fairly common case in data science, which is what I was saying. And here, accuracy is not a good measure for assessing model performance. Okay, so very important that this lecture is extremely important. Okay, because it's going to be the fundamental way that I'm going to try to, you know, break your analysis. So intuitively, we know that finding all negative data points in the terrorist detection problem is not helpful. And instead, we should focus on identifying the positive cases, right? You know, the disease cases, the 19 terrorists, etc. So the metric our intuition tells us we should maximize is known in statistics as the recall, which is the measure that I had shown before, which is, you know, you can think of it as the ability of a model to find all relevant cases within a data set. Okay, all relevant cases within a data set. So let's take a look. Also, I'm sure maybe you have seen this from the point of view of true positives, false positives, false negatives, true negatives, right? So that's a common terminology also. So that's why I like to introduce both of them. So here, but this is very similar. What I want you to understand that this is very similar to this. Okay, it's just a little different notation. So here we have the same thing. We have the predicted values over here and the actual values over here. And then we have positive and negative, positive and negative. And then obviously, you know, for an actual and positive and a predicted positive, that's going to be the true positive in green, right? And for a negative sample, a real negative and a predicted negative, that's going to be the true negative. And then the other ones are just going to be false positives or false negatives. Okay. So and here we can see the equation down here as well. So the precise definition of recall is the number of true positives, okay, divided by the number of true positives plus the number of false negatives. Okay, so these two. Okay, so very similar to what we had talked about out of the actual, how many were predicted. Okay, so true positives are data points, are data points classified as positive by the model that actually are positive, meaning they are correct. And false negatives are data points the model identifies as negative that actually are positive. Okay. In the terrorist case, true positives are correctly identified terrorists, and false negatives would be individuals the model labels as not terrorists that actually were terrorists. Okay, so that's what's important there. You miss some. And that comes into the point of how critical is that to miss something like that, right? So in disease detection, missing the disease, for instance, or something like that. So recall can be thought of as a model's ability to find all the data points of interest in a data set. Okay, and here we can see the formula for recall. So it's just going to be the true positives. So true positives, right? This one divided by true positives plus false negatives. So this one divided by this one. Okay. All right. And that translates for the terrorist detection problem into terrorists correctly identified, right, divided by terrorists correctly identified plus terrorists incorrectly labeled as not terrorists. Okay. So that is recall. All right. So how can we find all terrorists? In this case, let us predict everyone is a terrorist and problem solved, right? But that's not good because you're labeling what, 800 million people, and that doesn't work either. So recall here will be high because you didn't miss anyone, right? But then the problem is, in the case of recall, when we increase the recall, we decrease the precision. And we don't want that either, right? So we don't, because that's also not, labeling everyone is, you don't have the resources to handle that. Again, we intuitively know that a model that labels 100% of passengers as terrorists is probably not useful because we would then have to ban every single person from flying, and that just doesn't make sense. So this approach would suffer from low precision or the ability of a classification model to identify only the relevant data points. Okay. So that brings us then to precision. To look at the logic for precision here. So here again, it helps to look at the table, right? To look at the table of true, of this. So precision is defined as the number of true positives, again, divided by the number of true positives plus the number of false positives. So out of all of these, so out of all the predicted, how many actually work? Okay, not out of all the real, but out of all the predicted. So precision is defined as and I just said that. So false positives are cases. False positives are cases the model incorrectly labeled as positive that were actually negative. Or in our example, individuals the model classifies as terrorists that are not. Precision expresses the proportion of the data points our model says were relevant and actually were relevant. Okay, so in this case, we have true positives divided by true positives plus false positives. So in this case, from the terrorist scenario, it would be terrorists correctly identified divided by terrorists correctly identified plus individuals incorrectly labeled as terrorists, right? And that's going to be precision. So as you can see, there's a specific logic. There's a specific logic to all of these, okay? As we try to, as we evaluate the performance of a model, then we have accuracy, precision, and recall. And the confusion matrix is actually this table, right, that we've been analyzing. So it's very helpful to take a look at these. So now we can see that our model, which labeled all individuals as not terrorists, wasn't very useful. That's accuracy. Although it had near perfect accuracy, it had 0 precision and 0 recall because there were no true positives. Say we modify the model slightly and identify a single individual correct as a terrorist. Now our precision will be 1, but our recall will be very low because we will still have many false negatives. So if we go to the other extreme and classify all passengers as terrorists, we will have a recall of 1. We'll catch every terrorist, but our precision will be very low, and we'll detain many innocent individuals, right? So that's the key here. So in other words, as we increase precision, we decrease recall, and vice versa. Now, there are some legitimate cases where you really just want really high precision for whatever reason, right? Let's say that you just want to make sure that you capture everything of interest, and then you're going to filter it further. There are valid cases, but in general, one affects the other. And this is why that kind of motivates why we have a metric that combines precision and recall. All right, and that is called the F1 score or F measure. So in some situations, we might know that we want to maximize either recall or precision at the expense of the other metric, and that's perfectly valid. That might be something that in your term project you end up doing. You know, it just depends. It will depend. It's almost philosophically. It depends on what it is that you are trying to do with your problem, with your machine learning algorithm. For example, here's an example. In preliminary cancer screening of patients for follow-up examinations, we would probably want a recall near 1. All right, we want to find all patients who actually have cancer, and we can accept a low precision if the cost of the follow-up examination is not significant. All right, instead of losing, you know, a person or so on. So there are valid situations for that. However, in cases where we want to find an optimal blend of precision and recall, we can combine the two metrics using what is called the F1 score or F1 measure. Okay. All right, so the F1, and here we can see the formula. You can see that what's important about it is that it combines. First, we have to calculate the precision, then the recall, and then we combine them together. F1 measure is defined as the harmonic mean of precision and recall, taking both metrics into account, you know, by using the following equation. So here's a little bit more about this. It's actually an interesting function. We use the harmonic mean instead of a simple average because it punishes extreme values. Okay, so what that means is a classifier with a precision of 1 and a recall of 0, right, has a simple average of 0.5, which is not very meaningful. But if we use F1, which is a harmonic mean, the score is 0. Do you see that? So it penalizes extremes, basically. So the F1 score gives equal weight to both measures. But here, you know, the F1 score is the most commonly used. Okay, and then the weights can be adjusted, etc. If we want to create a balanced classification model with the optimal balance of recall and precision, then we will try to maximize the F1 score. So when you're training your model, as you're training it, you know, your goal is going to be then for an F1 measure to be pretty high. Is this clear, guys? Are there any questions? Nope. Yes, sir. Go ahead. Yes. We can actually. That's a very good question. When you have a balanced data set, calculating overall is fine. But let's say you have 4 classes or 10 classes, you have a highly imbalanced data set. It is actually strongly recommended that you calculate the metric for each class. That's actually a very good answer. I'll show you how to do that with Weka today. Do you see what I'm saying? Did I answer your question? Yeah, so that's a good one. Yes, definitely. You should do that, as I said, in your term project. I expect you to do all these things. Okay? All right, very good. So that's that one. All right, so now let's just get into a little bit of like the technical aspects. So performance evaluation. So, you know, as I said, evaluation of performance of your classifiers is extremely important. So far all semester, I've only just stressed, you know, accuracy basically, right? So I kept it pretty simple. But now we need to, hopefully now you understand why accuracy is not actually always a good one. And so we got to look at the other ones. As I said, I don't really cover sklearn in this class, except for like today, because, you know, for a few handy things that you can do with it, right? Just to point out that that's available, although PyTorch will have its own as well. So the sklearn kit provides very good modules to address this issue. In particular, evaluation often involves measuring accuracy, precision, recall, and F measure. The best way to understand these metrics is to think of a confusion matrix, which is what I showed you. Confusion matrices show how many elements from a class are correctly and incorrectly classified. Here is the code. I'm pretty sure this is in my GitHub. So you can just get it from there. Just go to the sklearn repository. You'll find all of these. So I'm not really going to demo it in class. You can just use it. But if you notice, what I have in here is, or you could literally just write it on your own. The sample code to obtain the metrics is basically a little function. Print stats percentage train test. If you notice, you can, an optional algorithm name, Y test and Y pred. What is this? Remember, the model predicts a set of labels, but then you have the real label. Remember, we did this last week. So that's what that is. So here you can see I'm just printing out the algorithm. Then we have print accuracy, right? And basically, this is the name of the module in sklearn, accuracy score. So accuracy score will take Y test and Y pred. Remember, these are the labels. They're probably column vectors, right, of the classes. And basically, it does, that's the same thing we did in class where, you know, this column equal this column and returns the truths and then, you know, does the calculation. To do the confusion matrix, we called confusion matrix over here. Do the same, Y test, Y pred. And then you can, you know, print it. You can use pandas so that it looks nicer. That's all that's happening here. This prints it in a, like, not a very friendly, readable approach. But if you do this pandas trick over here, it'll look a little bit nicer. Then precision, so that's precision score. Again, it just takes Y test and Y pred, nothing big. Recall, same thing, recall score, Y test, Y pred. And then finally, F1 score, Y test, Y pred. So basically, I will leave this function for you guys to develop. Okay, you can develop it with PyTorch, you know, sklearn, however you want to do it. You could even literally, you have the equations, you could write your own functions with NumPy, you know, if you want. So I leave this exercise to you. But going forward, or just get it from my GitHub, it's there. But just make sure that you have this going forward, all right? As part of your arsenal now, whenever you get a homework assignment, right? Not for the one due to 90 examiners, but going forward. Although if you want, actually implement even for, you know, the homework will stay open until Wednesday, right? So currently you'll probably reporting just accuracy, but now you should be able to report the other metrics as well. Does that make sense, guys? Is this clear? Raise your hand if you have any questions. All right, so it seems like this is clear. Good. Perfect. So here's just a code explanation of the previous thing. So I just did that. So that's a function, you know, two sets are provided, Y pred and Y test. As you know, Y test is the original annotated labels. Y pred is the labels predicted by your classifier. And then the metric functions were F1 score, recall score, and so on, which take two data sets, the true and the predicted. Right, perfect. So that is the metrics, okay? So let's go ahead now and let's take a look at, I'm gonna discard these. All right, so let me, this is still recording, so let me switch to the, all right, so we're back on Brightspace. So I think some of you were came in late or something. So I just want to remind you, I've uploaded the term project module, okay? And I provided the link here. This is the data that we're going to use. This is real world data called ADS-B exchange data. This data of the transponders of aircraft, but the new technology, which is digital. Okay, so all the planes at least in the United States are using this now. Okay. Anyway, so make sure you work on that. And there's going to be a part A and a part B. All right, so we've completed this module, performance metrics, right? Those slides are done. So now I'm going to actually move this here. So we're going to look at the Weka tool, which is really great to kind of motivate what I've discussed. So I have some slides here, and then we're going to actually use the Iris data set to play with this, and it should be pretty quick. And then after that, I just want to do a really quick lecture on traditional machine learning. When I say traditional machine learning, I mean like the other algorithms, not the deep learning ones. There's a few other ones. I'm not going to get into the theory of those. There's a class we have called ITS 365 Machine Learning Foundations, where I literally write the code for every single one of these algorithms. So if you have an interest in that, the fundamentals, take that course. But in this class, because this is more applied machine learning with deep learning, I really want to focus more on problems. Okay, you have the code now, so you should be able to just solve problems going forward. Remember, you have this ADSB data now. I expect all of you to have really interesting results. I mean, if you think about it this way, I want to give you this motivation. You're all grad students, right? You all want to do a little bit of research or something like that. That's real data. If you come up with a nice problem, if you look at a lot of data, you can literally even publish that, right? We can talk about submitting your papers somewhere, depending on the quality of it, if it's at a certain level. Okay, so it's certainly an opportunity to do very good work. ADSB Exchange, as I said, is 2-3 years old at most, and it's going to revolution. I mean, it's going to be very necessary for the drone industry, general aviation, and a lot of other things. It's data that wasn't there before, and now it's there, so there's opportunity. All right, so now I've completed the performance metrics, the theory of that. Now I want to look at Weka. All right, so Weka, here I have a little bit of, what do you call it? A slide, basically. So we're going to take a look at that one. Oh, actually, I can't write on this. So, okay, it'll open in a second. And then I need to switch. Okay, so I'm going to switch to Weka. All right, there it is. All right, so this is the Weka tool. It's a tool that has been around for 20 years, probably. Okay, it has now deep learning functionalities. I think it's still written in Java, although I hope they switch away from that to like C or something. It's developed by the University of New Zealand. It's a really great tool that you know, it's been used widely. Okay. And it's very nice, I think, for our purposes to kind of visualize things really quickly. As I said, my recommendation to you, let's say you had terabytes of data, you know, a billion records or whatever. Sample the data, sample about 100,000 of those records a few times with no more than 10,000 columns, and you should be able to run it on Weka efficiently and visualize your data, get a feel for what you are seeing. So what is Weka? Weka is a Java-based program for machine learning. All the algorithms are implemented, but it's got a GUI interface. So it's not like, you know, coding. It doesn't require any coding, in fact. It's just like point and click. Okay, so very good for visualization, for quick prototyping, quick assessment. So certainly for the type of data sets that you'll be looking at in this class, you should totally use Weka. It's easy to use, so it'll take us, by today, you'll be experts on it, right? So it's very easy to use. It's GUI based, as I said. All this I just said. So for quick prototyping, not really for big data, but pretty good. You know, you solve it by just sampling the data. This is what it looks like. So that's the basic menu for it. GUI, it's got a couple of interesting features. The Explorer is the one we're going to mainly use. However, there's something called the experimenter. And the experimenter is, so if you ever, you know, they're in machine AI, right? There's two groups. There's the machine learning people, which are more experimental, right? The coders. And then there's the statistics people, the mathematicians, statisticians. And they're more sticklers on the statistics. And, you know, you guys took your statistics class and you learned about the p-value. Remember that? The p-value and the confidence interval and all that stuff. And so when you report and you say something like, yes, I ran 3 algorithms on my data set, and I say this one's the best. And you think it's the best because it was like 5% F measure was better, right? And I said that that's good. Well, but a statistician will say, yeah, but what's the p-value for that? You know, what's the level of confidence or the confidence interval? And so the experimenter, this one over here, does that for you, okay? This one, you'll be able to set up an experiment with the same data set, let's say 3 algorithms or however many, and then it's going to conclusively say, yes, this one is better, and here's the p-value. And so, yes, there's a significant confidence that this is the correct one. You see, do you guys see that? You understand the difference? So that's what experimenter is for. But mostly, you know, if we just want to not do that, Explorer is good enough. And then there's these other ones. This is like a command line. This is more like a even more GUI, and so on. So you can play with these, of course, if you want. But I'll just, you know, basically be going over this one. This is what it looks like. This is called the Explorer. So we'll open that window, load a data set, play with it. Data formats. So far you've learned, like for PyTorch, that we could load CSV files. You learned you could load images. You learned you could load, you know, those types of data sets. But there's a lot of data sets out there. Weka has a specific data set called the ARF data set. But you can easily just load a CSV file, and it accepts other formats as well. You can actually even take a CSV file and convert it to ARF. So it's got that option. Questions, guys? All right, the features or classes. We have basically, for the classes, they can be numeric or nominal. All right, for classification, we're going to need them to be nominal. If the classes are numeric, it's going to treat the problem as a linear regression. Okay, so for it to treat a problem as a classification problem, you have to set the class column to be what is called nominal. And I'll show you guys how to do that. But that's a common problem. The classifiers, one of them is called the decision tree. Basically, it's a classifier that starts based on the features. Let's say feature 1, it decides a cutoff. If the value of feature 1 is less than 0.5, then I'm going to look at feature 3. If the value of F3 is like 0.2, then I'm going to look at F6. Otherwise, I'm going to look at F4. These are the features, right? The features of a sample. So like, you know, height, width, whatever, and so on. So what a decision tree does is it creates a structure like that, almost like a whole bunch of if statements. After there's an algorithm, obviously, and everything, but that's the idea. In Weka, decision, as I said, I'm not going to go into these different algorithms. All right, that's a topic for the Machine Learning Foundations class 365. But here we're just going to use this classifier. It's called J48 in Weka. Yeah, the T statistic, this is what is related to the experimenter, what I was talking about here. So that slide is a little bit out of place. Feature ranking is another nice feature that Weka has. We'll take a look at that one. So what feature ranking does is it identifies what are the best features in your problem. You see that, let's say that you guys want to figure out how to grow tomatoes, right? Or avocados or wine or whatever, right? In a farm. And you just want to, you know, you want to predict something, right? You know, my production is going to be good or bad. You know, I'm going to produce more than 1 million, I don't know, fruits or less, right? So you're going to have some features that you've collected, right? So, pH balance, amount of rain, how the wind, how fertilizers, all that stuff. Those are your features. But you really don't know which one of those is the most important. Maybe at the end of the day, it's just amount of rain, right? That might be the thing that determines. But how do you know that? How do you know that, right? Well, as it turns out, the feature ranking, giving a data set, an annotated data set with labels, we can do feature ranking and figure out which one of the features is the best. You guys understand that? And so Weka can do that for you as well. So that's very handy, because then focus on not spending so much on fertilizer and just irrigate, that kind of thing. Okay, so scratch that out. But so the process is going to be basically to load our data set, make sure that the class is converted to nominal so that it's a classification process. Maybe you need to do a little bit of filtering of your data, then select one of the algorithms, measure the performance, and use feature ranking. This is the pipeline basically in Weka that you should be doing, going forward for all your project assignments or homework assignments. Even though you're going to be implementing PyTorch, etc., you should always grab a sample of your data, run it through Weka. Make sense? You can do all of this in code, but the advantage of Weka is it does it for you very nicely. All right, so that's it. So let's see. It is currently 3:24. So let's take a 10-minute break. We'll start at 3:35, and when we come back, we'll go over Weka. So we'll load the iris data set, and then we'll just play with it. Okay, got it? All right, so let's take a 10-minute break.